Let me show how to view local variables in a release mode optimized application. Alright, so this is the scenario. Imagine you have to debug an application in production, but it is release mode, it has stripped symbols, and it is optimized. Often, this is the case, and it is very difficult to debug. So let me show you one technique to view local variables even though WinDBG says there is none. This works for memory dumps as well. But for this demo, I'm going to use a live application because I need access to the source code. Let me switch over to Visual Studio. This is a view of my application in Visual Studio. The application means nothing. It's just an MFC application that is just the sample MFC application. What I want to do is put a breakpoint in the function on init dialog. When I run the application and put the breakpoint, I would like to see these three variables in WinDBG. And this is where the complication begins. Before we run the application, let's go over some of the properties of the application. So when we build this application, there are some settings that if we have these settings enabled, it'll make debugging a bit more easier. The first option, which is the simplest to set, is to just disable optimization over here. The problem is that most release mode application is going to be optimized. So I'm going to leave this option enabled even though it makes debugging harder. The next option is to try to get full symbols. I will be using stripped symbols for this demo to be more authentic because a lot of times when you have a release mode application, these symbols will be stripped. Finally, the option we absolutely need is to set the assembler output over here under output files. If we do not have the assembler listings over here, it is still possible to use WinDBG, but it is a whole lot more tedious and complicated. So let's go with having the assembler listing so that at least it is not as tedious as it can be. Okay, so let's switch over to WinDBG. WinDBG is already running attached to a process and has hit a breakpoint. Even though WinDBG has hit a breakpoint, we can see that no source code has been opened. This is correct because when the symbols are stripped, WinDBG is unable to find the location within source code. So we will have to drag in a file and open the source code ourselves. Let me just do that really quick. There we are, the source code has been loaded. Now within the source code, the breakpoint is actually located here on init dialog. We can't see any indication in the source code because WinDBG is unable to match the line from here to where the source code is. However, we can confirm the location by going into the view and opening the disassembly window. If we open the disassembly, we can see that it is highlighted that we are at the breakpoint of on init dialog. Now, if I run dv over here, I'm gonna get no symbols. This is correct because the symbols are stripped and we are still at the breakpoint on top of the function prolog. So what if we run the debugger until the end of the function and then try to view the local variables? So we can jump to the end of the function by doing pt, which goes to the end of the function. We just run it 2 times because WinDBG is kind of waiting at the first breakpoint. And we end up at the ret, which is the end of the function. At this location, we are already past the function epilogue. So the problem will be that even if there were local variables, if we run dv and we had full symbols, we still can't see the local variables because the function epilogue has already occurred. So with this, how would we possibly view the local variables? Let me show you a technique. So let me start the application again. Let me just restart it back to the start. And I'm just going to run it to the first breakpoint, back to on init dialog. Within the assembler, we know that the local variable should be after the sub instruction over here. This is because we know that the local variables are going to be allocated by subtracting from ESP. However, when I view the assembler, I can't really spot anything in here which is local variables. And that is intentional because when the code is optimized, it's very difficult to spot the local variables after the sub. So what can we do about it? So this is where the assembler listings comes in. What we can do is we can view the assembler listings to find where the local variables are and then inspect the memory at that location. So because we added assembler listings in Visual Studio when we compiled, If we go over to the folders on the disk and go over to release, we will find these COD files, and these are the code listings in assembler. Let me just open the COD file for this file over here which we are viewing. The file will contain the assembler listings in this format. The assembler listings file is made up of many sections. There's a header over here, there are function descriptions over here, and there is assembler at the bottom. We don't need to care too much about the sections because we're just going to search for the relevant lines that we need. So how we do that is we switch to WinDBG, and then we find one of the lines that initializes a local variable, and then we try to find this line in the assembler listings. Okay, let me search for it. We can see that the line cannot be found in the file. This means that the line has been optimized away. So let's try with a different variable to see if we can find any variable on the stack. Let's switch back to WinDBG and find another line. Let's try the second line instead, which is the string value. The string value also cannot be found. This is correct because many variables could be optimized away. Let's try one last time with the final line in WinDBG, which is the line that is initialized to a random variable. When I search for this line, I am finally able to find something in the file that indicates that the line is being compiled. How we read this file is quite important. The line over here with the semicolon in the front means that this is a line of source code. This is line 80 and this is the C++ for this line. If we scroll a bit down, we see that this line is repeated one more time over here. This is correct. This means that the assembler for that line is more than one block of assembler. How we read the assembler is as follows. Under every line of code, there will be an address over here, and there will be the lines of assembler. These numbers are the actual instruction that is being compiled. Below the instruction is the English representation of the instruction. These words over here is exactly the same as this. So we can read this as inference of what this means. So from here, I can see that the first line is a call to the function rand, and the result of that is being put into the location over here, which is the actual value of the variable var change. So if I take this address and I look in WinDBG, I should be able to find the value for var change. Now this address is a code address, but it is not an absolute address, it is a relative address. So let me show you how to use this address. Let's just copy it and go back to WinDBG. So what we do with the address over here is that we put a breakpoint, but because this is a relative address, it is actually relative to the start of the function. So we just take the address of the start of the function and we add it, and we just put a breakpoint here, and we will get a breakpoint within the assembler over here. Now, if we run the program to that location, like that, we will hit this breakpoint and we will be able to see the local variable. Now, the return of the rand function will be in the EAX register. We know that because all function calls end with the return in EAX. So the value of the EAX register, which is 29 hex, is being stored into the location EBP-1C. This is the location on the stack that contains the value for var changed. Now, if I step this instruction one time, I can actually view the variable over here, and I can get the value 29 hex. So I can just view it in decimals, and it's the number 41. The other two variables over here, they are missing because they are actually constant. We can actually prove that. If I go down the function, I actually have a line of code over here which we output the value of all the variables. So we can put a breakpoint on this line and we can actually view the other variables to prove that they are constant. So like before, if we search for this line in the assembler listings, we should be able to find this line, and we can look at the assembler instructions. What we want to do is we just want to get the address. So this is the address over here. So if I switch back to WinDBG and I search for this address, I should be able to find that part of the assembler. So as before, it is a relative address. So let me just put the address over here. And we will be able to put another breakpoint in assembler. Let's just scroll down to where the breakpoint is. We see two lines that are highlighted, but it's actually the same memory address. It's just a bug within the viewer itself. So if we run the program to that location over here, we now can see that the value of this instruction is being changed from a memory address to a register. Now, what is happening is that the optimizations are kicking in. In release mode, especially optimized, sometimes when we have instructions that need to manipulate memory, the memory will be loaded into a register, in this case EBX, and then the add instruction is being added to EBX, which matches the source code. The add instruction over here is adding int value, but we can see that the value over here is not another memory address. That is correct because int value is actually constant. So if we view int value in formats, it is actually the number 12, which is the same as the number 12 over here. So if I run the debugger a couple of lines after the add, I can see that the result is stored in the EBX register. That is again correct because when calculations are done, sometimes the optimized code does not actually put the value back into the stack, it just leaves it in the register. Finally, if I want to view all the variables, because I have a line here that views all the variables, what I can do is I can copy this line and I can search in the assembler listings. So in the assembler listings, when I search for that line, I get the value over here and I see that it is a block of assembler. Let's just jump to the end of the block, which is the final call over here, and I will set WinDebug to go to that location. So as before, we just put a breakpoint and we just run the debugger until we reach that location. From here, we can see that the call that we want, the call to format, has got a lot of parameters. Now, parameters that are passed into a function are passed from right to left. So if we look at the call to format, we see that the parameters are a string, int value, string value, and var changed. But on the stack, it will be pushed as var change, string value, int value, followed by this string. So within the assembler, we can spot that push EBX is var changed. We can see that push this value, which is the string value, we can verify that by just doing du and we get string value. And we can see that the number OC is being pushed as int value. And we can see that there is one more push over here, which is the actual value that is going into the string. So du, here we see value is d as d, which is exactly the same as this. Now we can actually see the contents of str message by just stepping through the assembler a couple of times. So if I step past the push line over here, the value of EBP18H, if I run dt string on that location, I will get the contents of the C string. The reason I can put C string here is because dt takes in a parameter where we can just force whatever type we think it is. Now I can see that the answer is value is 12, string value is 53. If I run the debugger a couple of times to pass the output debug string, which is this call over here, I get the same identical result that will come out. Let me just scroll up to find the result. There we are. Value is 12, string value is 53, which is identical to the contents of the str message. Well, that was pretty tedious. That is the technique that I use to view local variables within a function. The technique basically is view the assembler, find where the local variable is being manipulated, put a breakpoint exactly in that location, and then just view the memory for that location. This technique always works if you are able to figure out where the memory is being manipulated. This would have been a whole lot easier if there was a built-in command that could just view all the memory like dv. But the issue is that sometimes the optimization moves the memory around from a location on the stack to a register, or sometimes it is just optimized away. This is why putting the breakpoint means I can exactly see what exactly that line is to deduce how to view the memory. It is possible to try to deduce where the variables are without the assembler listings, but it is a whole lot more complicated and tedious, so I did not want to do that for the first attempt. Anyway, comment below if you have ever attempted to view local variables without using full public symbols, and let me know how it went. Gentle reminder to subscribe, hit that bell icon and give a like if you like the content. As always, it's been a pleasure bringing you this information. I am High Voice, signing out.